Hello, can you hear me?
Yes.
Okay, I'm waiting for my partner, Tamia. Tamia, are you there?
So I'm here.
Okay. So we decided to compare LZW's algorithm and Huffman's algorithm for cybersecurity programs in their implementation. Okay. So to begin our abstract, cybersecurity was definitely a word that's been used on all domains, just across the internet, and attained an enormous amount of attention. Um, Rapid cybersecurity attacks forces the government and private organizations to create and support the awareness of cyber threats and various versions of cybersecurity. So in this PowerPoint, we will further discuss how encryption is commonly used as a tactic in cybersecurity, the importance of encryption and compression algorithms, and the comparison of the two most commonly used algorithms for encryption, which is Huffman's algorithm and LZW's algorithm.
For our introduction, in today's society, cybersecurity is very important. Mia, you might have to mute yourself so it won't echo.
Sorry.
Most people don't understand the true meaning of cybersecurity. Cybersecurity highly values the use of encryptions and compression algorithms. This established the protection of the private and personal data through the use of unique codes to scramble personal and/or private data. Many businesses value the use of encryption because they are collecting private user data information. In order to prevent unauthorized agents from gaining access, many corporations will value cybersecurity by ensuring that they encrypt all data in their possession.
So furthermore, some reasons why many companies need to value cybersecurity and data encryption is data in transit is highly vulnerable. So hackers can easily attack communication channels in order to capture the data in the transit, data in transit. Some security threats are consistently evolving by attackers constantly learning and identifying new ways to get past the toughest and tightest cybersecurity defenses. The installations and the use of uncertified online resources and applications can increase intrusions and security breaches and expose highly sensitive data. And hacking became a highly competitive business throughout business rivalry, from their competitors gaining access to private data to learn the next business's moves and goals.
All right, so we did the background of the LZW algorithm. LZW is named after Abraham Lepel, Jacob Zeev, and Terry Welch, who made sure that it was perfected within the algorithm. In 1978, Lepel and Zeev published a bulk of papers which had the description of the compression algorithm and separated the dictionary of the LZ78 algorithm. In 1982, Welch began to develop the simple algorithm based off the LZ78. He worked on the compression algorithm in order to assist with the high performance disk controllers known as the LZW algorithm. LZW algorithm compression was created to replace the strings of the character codes. Also, the algorithm adds all the new strings to a table.
Here we have a sample code of the LZW compression algorithm, but this code is to put it in layman's terms. That way, those that are not computer science people or IT people can further understand how this compression algorithm was created. And here is the flow chart This is also the same thing, kind of putting it a little more layman's terms, but giving more of a picture of how the LZW compression is worked. This will be further explained. So in cybersecurity fields, compression algorithms are typically used for encryptions. LZW algorithm will identify the repeated sequences and add them to a code table. So compression will start when the second time a sequence is encountered, then the compression of the variables continue until a match is found. So when the match is found is in the table, no action is needed before determining if there is a longer matching sequence in the table. But if there is not a longer sequence in the table, then the algorithm should add it to the table and output the code for the shorter sequence that is in the table. This is continued until there is no more characters in the input file.
All right, and then here's the LZW decompression, a sample code of this. Like she just explained in the earlier one, that this is just a sample code, just shows that, like she said, the people who aren't as technical, it just shows you like a sample of the breakdown, how everything is going to be as a code. And then here's the flow chart for the decompression flow. This is the LZW decompression flow chart. It'll be explained further in the next slide, but we also have the link to the codes that goes along with the flow chart on the side if anyone is interested.
That is also for the compression algorithm as well. They're both the same code.
Yeah, they're both. Yeah,
it's just an overall.
So the explanation for the LZW decompression flowchart. In cybersecurity fields, decompression algorithms are typically used for decryption. First, the decompression algorithm will take the first byte from the input file and place it in a variable in order to output. The algorithm will continue to loop for each additional byte in the input file. Every time a byte is read from the input file, it is then stored in another variable. The data table is continuously searched until it finds a new variable to output. This process is continued until the last input is reached.
So in this slide, we analyzed the LZW's algorithm. So we noticed that their main advantage of this algorithm is for files that contain a lot of repetitive data. We also noticed that it's often used with text and monochrome images, and that it's known to be one of the fastest compression algorithms, although it is a fairly old compression technique. Nowadays, recent computer systems have the horsepower to not only use the LZW's compression algorithm, but to also use it with more efficient algorithms as well. We also realized throughout our research that typically the LZW's algorithm is used in tagged image files, format files, graphics interchange format files, PDF files, and a variety of other file formats. We created this LZW's algorithm to improve the compression ratio and reduce computational complexity. So throughout our research, we manually built our LZW's program in both C++ and Python. And this has proven that LZW uses a dictionary in order to encode and decode. And that'll be further shown after the presentation.
So we did another algorithm, which is the Huffman's algorithm. So here's a little just a background of the Huffman's algorithm. In 1951, as a student, David Huffman decided to write his term paper about finding the most efficient and optimal code in order to avoid studying for his electrical engineering final. In his discovery of this algorithm, he discovered that the most optimal code would need to have the lowest possible average message length. He called this the greedy strategy. The strategy would sometimes produce the most optimal solution and sometimes it wouldn't. This is because the algorithm is based on the frequency of the characters appearing in a file. This strategy is oftentimes represented through a binary tree. All right, so here's an example of the Huffman's binary tree. It breaks it down pretty much, just the codes and with the probabilities, and it just breaks it down all into a tree, and then which way the different probabilities and codes will go. Here is the flow chart for the Huffman's algorithm. And as we stated before, we have the codes on the side, the link to the codes if anyone is interested in going to take a look, but it follows the same exact way of the flow chart. So it follows the same exact else if then statements, but in a flow chart form. And it's going to be explained after this. So the explanation of Huffman's flow chart. Huffman coding uses the frequency of letters and text in order to calculate the sort in the characters in the most frequent and least frequent. When encrypting, they calculate and sort the letters. The Huffman algorithm will then create a tree with the leaves based on the letters and the value of the weight. In order to create this tree, you look for the weakest nodes with the smallest weight and connect them to the new nodes. This new weight will be the sum of two nodes. Then repeat the process until there is only one node left. This will become the route, the weight, and then the total number of the letters in the message. When decrypting, you match the tree dictionary by match the characters with the proper binary code. And then here's an analyst of the Huffman's algorithm. To encode information by using variable length strings to represent symbols depending on how frequent they appear. Throughout our research, we manually built our own Huffman's program in a C++ or Python, which we showed the two links at the bottom previously in the previous slide. Proven that it is used for compression by applying the algorithm to the most recent characters, which are coded with similar binary words. The size of the code, minimally increases compressions. Two encoding families are static and adaptive Huffman algorithm. Static calculates the frequency first, calculates the frequency first, then generate common tree for both compression and decompression. Adaptive develops the tree while calculating the different frequencies, while there are two trees within both processes. So within the analyst, we developed the idea that the symbols are used more frequently should be shorter, while the symbols that appear more rarely can be longer. And it comes in assistance with establishing the number of bytes and to encode to a given message to shorten the message.
So here is our comparison of the LZW versus the Huffman's algorithm when it comes to implementing cybersecurity programs. So due to the advancements in coding and technology that occurred between the creation of Huffman's algorithm in 1951 and LZW's algorithm, which was created in 1978, LZW was developed to require no prior information about the input data stream. It has the ability to compress the input stress through one single pass. Then, due to these improvements, LZW's algorithm became very simple and very fast, had a very faster execution compared to Huffman's algorithm. So, me and Tamia, we further analyzed the big O notation of each LZW and the Huffman's algorithm. And so the time complexity for Huffman's algorithm was the big O notation of n log of n, and the time complexity of the LZW's algorithm was the big O notation of n. So after comparing these time complexities, we noticed that the LZW is less than the Huffman's algorithm. Therefore, this algorithm executes faster.
Our conclusion for future cybersecurity enhancements. LZW's algorithm is proven to the most efficient for future cybersecurity programs. Due to the big O notation, time complexity is low and leads to a faster execution time. Faster execution times allows for private information and data to be protected faster and prevents cybersecurity attacks from occurring. LZW algorithm is widely used for universal data compression methods. They will lead to continuous improvements and enhancements to improve the overall compression ratio and the reduction of computational complexion. Improvements will further lead to the reduction of storage hardware, data transmission time, and communication bandwidth for the government and many other private organizations. This will result in cost saving and decrease in expenses and primary data storage.
Here is our bibliography, and thank you for your attention. We're now available for questions. I'm also going to show some of the code as well. That way you all can see how it implements.
You're on mute.
There we go. So this one is the Huffman C++ code. It shows, the statements. And then if you was to run it, well, here's the entire code if you guys want to see it. And then if you was to run the code, it show you the implementation and it shows you the execution, but it also shows you the original string, which is the Huffman code, and then it shows you the encoded string and the decoded string. So this is just one example of our code.
All right, thank you. Next person, please.